Section 2.3 is linear first order differential equations. So we're going to look at the definition of a linear equation. We'll look at a method to solve first order linear differential equations. We'll look at a couple of examples, and then we'll look at a few examples just for classifying to see which ones are linear, which ones are not. First, the term linear is first defined in section 1.1 in the book. If you have a linear first order differential equation, the standard form is you have dy over dx plus p of x times y equals q of x, where p of x and q of x are functions of x. Notice that the terms that involve the dependent variable y are this p of x times y, which is linear, regardless of what p of x is. Y is raised to the first power, and then the derivative of y, which is also raised to the first power. So this is a linear first order because we have a first derivative equation. And if you have a linear first order equation, you can introduce what's called an integrating factor. So the integrating factor looks like this. That d of x should be up here. E to the integral of p of x, integrate with respect to x. When you do that and multiply through, you multiply both sides of the equation by that integrating factor. Then the left side becomes, this is our mu of x, is the integrating factor. You get mu of x times dy over dx plus mu of x times p of x times y. On the right side, you get mu of x times q of x. But notice that what we have here on the left side of the equation can be written as a single derivative, the derivative with respect to x of mu of x times y. Here, you can use the product rule to take the derivative and let me erase that. And you get there. And you get the derivative of mu of x with respect to x. That's going to be mu prime of x times y plus mu of x times y prime. So when you introduce mu of x, well, so let's see what we have here. We have mu of x times the derivative of y, that's this term right here. And then the second term, mu of x times p of x times y. So there's our y. The question is mu prime of x equal to mu of x times p? We know that mu of x is e to the integral. So let's do that. Mu of x is e to the integral p of x, d of x, p of x. So this is mu of x. What's mu prime of x? So when you take the derivative of an exponential, you take the derivative of the exponent, the derivative of the integral of p of x dx, is p of x. And then you multiply by that same exponential, e to the integral p of x dx. And notice that these are the same. We have p of x times that exponential. So the beauty of this lies right here, that by introducing that integrating factor, you're able to rewrite the left side of the equation as a single derivative. And then to undo that derivative, you integrate both sides of the equation. So let's see. Let's see how that actually works. Notice that here we have the general form for a linear equation. We've got dy over dx plus p of x times y equals q of x. In this case, p of x is 1 and q of x is 2x. And so we're going to introduce our integrating factor, which is mu of x equals e to the integral of p of x, that's 1, integrate with respect to x. And that'll give us e to the x. We're going to multiply by e to the x to get e to the x times dy over dx plus e to the x y equals 2x e to the x. So, and remember, the beauty of the integrating factor is that we'll be able to take these two terms on the left side of the equation and write them as a single derivative. And it'll always be mu of x times y. Mu of x is e to the x. E to the x times y. So at this point, you should double check your work just to make sure that these are equal. When you take the derivative of e to the x times y, you're applying the product rule for derivatives. The derivative of e to the x is e to the x. So you get an e to the x times y. That's the second term up here. Plus the derivative of y times e to the x. There's our derivative of y times e to the x. And so that checks. If it doesn't check, go back and make sure that you have your p of x defined correctly. So at this point, we want to undo that derivative by integrating with respect to x on both sides of the equation. On the left side, that integral and that derivative cancel out to give you e to the x y. On the right side, that 2 we could take out, but to integrate x e to the x, we want to integrate by parts. If we let u equal 2x, and then du is going to be 2 dx, dv is e to the x dx, and v is e to the x. So when you integrate by parts, integrating u dv gives you uv minus the integral v du. So I get u times v, 2x e to the x minus the integral v du, e to the x times 2 dx. So finishing that integration on the right side, when you integrate e to the x, you get e to the x. So that second term is going to be 2e to the x plus c. From here, I can solve for y by multiplying by e to the negative x on both sides. And that'll give me y equals 2x minus 2 plus c e to the negative x. And there's my solution. Remember, this is called a general solution. A general solution is one in which you still have that constant of integration, still have c, or an unknown value. So we'll look at the second example. Here we have an initial value problem. In this case, our initial value is pi. We're given y of pi is 0. We're told that x is greater than 0, because if x is equal to 0, this 2 over x is not going to be defined. And we'll also see why once we calculate this. Notice that this is in general form. If it isn't, you would rewrite it into general form. It's in general form where p of x is 2 over x and q of x is sine of x. So I'm going to introduce my integrating factor, which is going to be e to the integral of p of x dx. So that 2 will carry. When I take the integral of 1 over x dx, I get the natural log of x. Here I'm going to rewrite this as natural log of x squared using the power rule for logarithms. That 2 can come up here and become an exponent. And then e and natural log will cancel, so that I'm left with just x squared. My integrating factor is x squared. I'm going to multiply by x squared to get x squared times dy over dx plus 2x, that x squared over this x in the denominator will cancel to give me an x. 2xy equals x squared sine x. So the left side of the equation I can simplify by writing as a single derivative. And remember, it's always u of x times y. U of x, or mu of x rather, is x squared. So we get x squared times y. We'll verify that. The derivative of x squared is 2x, so I have 2x times y. That's this second term. Plus the derivative of y is dy over dx, and that's multiplied by x squared. So the product rule holds true. We'll integrate both sides with respect to x. That gives me x squared y equals the integral of x squared sine x. So here, again, I have to integrate by parts. U is going to be x squared, dv is going to be sine of x, dx. du is 2x dx. And v is the integral here. So that's going to have to be negative cosine x. Derivative of cosine is negative sign. So I have to cancel that negative. And we're going to get UV. So I get x squared times negative cosine x gives me negative x squared cosine x minus the integral v du. So I'm going to have minus a negative. That's going to make it a plus. I'm going to have 2x. I'll just keep that there. Cosine x dx. And I need to integrate by parts again. This time, my u is going to be 2x, and du is going to be 2dx. dv is cosine x dx, and then v is going to be sine x. So let me rewrite this. X squared y equals negative x squared cosine x. And then this integral becomes uv 2x sine x. So plus 2x sine x minus the integral v du minus 2 sine x dx. And then I can do that last integration. So I get negative x squared cosine x plus 2x sine x. And this is going to be minus 2. When you integrate sine x, you're going to get negative cosine x. We did that right here. And that negative will change this to a plus 2 cosine x, and then plus our constant of integration. And we can solve for y to get the general solution. Divide by x squared. I'm going to divide each term by x squared. You could choose to divide the entire side by x squared if you want to. But this will give me negative cosine x plus 2 over x sine x plus 2 over x squared cosine x plus c over x squared. That's our general solution. And we'll get the particular solution that corresponds to y of pi equals 0. So I know that y of pi equals 0. That means when x is pi, y is 0. So I get 0 for y equals negative cosine pi plus 2 over x is pi sine pi plus 2 over pi squared cosine pi plus c over pi squared. So let's see. Cosine of pi is negative 1. Sine of pi is 0. So this term drops out. And I have, I think what I'll do is I'll bring that 1 over to the left side. That's a positive 1. When I bring it over to the left side, it becomes negative 1 equals 2 times negative 1 is negative 2 over pi squared plus c over pi squared. And I'm going to multiply by pi squared first. to get negative pi squared equals negative 2 plus c. And then I can solve for c by adding 2. So c is 2 minus pi squared. Substitute that in for my c in my general solution. And we'll get our particular solution, which is y equals negative cosine x plus 2 over x sine x plus 2 over x squared cosine x plus c, oh no, plus c is 2 minus pi squared over pi squared. And I think I'll leave it just like that. And that's my particular solution. So there's two examples on how to solve linear equations. Anytime you have a first order linear equation, you would basically solve it the same way you would introduce an integrating factor. You could expect to see questions on the test, such as what is the integrating factor that would be used to solve this equation just like that. You would expect to see questions just like example 1 and 2, solving an equation that happens to be linear. And you could see questions like these 4, which is just identifying the type of equation you have. In this case, we've talked about linear from 2.2 and separable from section 2.3. Sometimes equations are both linear and separable. Sometimes they're just linear. Sometimes they're just separable. Or maybe they're neither. And we're going to look at 3 different types of equations in the 2 sections that remain on solving equations. So if we look at question number 1, you should be able to easily look at an equation and determine if it's linear. To be linear, your derivative has to be linear, and any of your dependent variables have to be linear, like y to the first, linear, y to the first, linear, y squared, not linear. Sine y, not linear. So these first 2, it's real easy to look at them and see that 1 and 2 are both linear, 3 and 4 are not linear. It should be that quick for you to classify these. And then for separable, remember that for separable, you want to be able to write the derivative as a function of x times a function of y. And number 1, you have a function of x times a function of y. So this one is also separable. On number 2, when you bring that y over to the right side, you're going to have dy over dx equals x squared minus y. If you have a plus or minus in between the terms, unless you have a common factor that will factor out so that you get a function of x times a function of y, it is not going to be separable. Here, there's no way factoring that you can break up the x squared and the y. So this one is not separable. Number 3, notice that you have a function of x in the numerator, you have a function of y in the denominator. So you could write that as your function of x times your function of y. This one is separable. And then the last one, if I bring that sine y over to the right side, I have my derivative equals x minus sine of y. And again, because you have those two terms subtracted, and the first term is only a function of x, the second term is only a function of y, you're not going to be able to factor out to get a function of x times a function of y. This is not separable. So notice this one is both. Number 2 is only linear, not separable. Number 3 is only separable, not linear. And number 4 is neither linear nor separable.